So, is it going? Yes. We have this tower. It's 128 stories. It doesn't matter that it's the tallest tower in China. And it doesn't really matter that it contains the fastest elevators. But the elevators run at a speed of 1,080 meters per minute, assuming that each story in the building is about 16 feet. So that's giving you a conversion right away, right? Each story is 16 feet. How many seconds will it take for a passenger to move from the first floor to the 120th floor? And then this part B here is how fast will the elevator travel in miles per hour? So for part B, we we know the speed of the elevator is 1,080 meters per minute. So for part B, it's really just a matter of converting the speed from meters per minute to miles per hour. So part B is basically just a normal unit conversion. Part A might be a little trickier. So what we have is we first need to figure out how tall the tower is, right? Um, and there's a few things happening that make it more difficult than it might seem. So it's 128 stories. So let's just figure out the height first. So height, it's a tower. Tower. So as I said, it's 128 stories, and each. Sorry for my hands, by the way. So many cracked skin knuckle things from all the hand washing. But it's 128 stories. Each story is 16 feet. So the whole total height is 128. And you could do this using unit analysis, like you could do 128 stories times, and then one story. It looks weird. One story is 16 feet. Stories cancel, and so you get feet. You could do it that way, but it also just makes sense, I mean, intuitively to multiply them together. So you'll get 128 times 16. So you get 2,048 feet. All right, so basically, we want to see how many seconds it will take for a person to go 2,048 feet at a certain speed. And that certain speed is the next part. So I'm given the speed in meters per minute, but this is in feet. So it probably would make the most sense to convert 1,080 meters per minute to feet per second, because then I can, using that relationship, I can then convert the feet into seconds using the speed of the elevator in feet per second. All right. So we have the height, and then the next part, as I said, is we want to convert the speed into feet per second. So 1,080, and then it's meters per minute. So again, per, when you read the word per, you should think of division. So per minute, there's no number there, so it's assumed to be one. So 1 minute. Right. And I'll convert that to feet. So how many meters in a feet? I forget. Meters in a foot. So let me write that down somewhere. So 1 foot equals 0.3048 meters. You need that, right? And again, I don't expect you to memorize these conversion factors, or these conversions. So don't worry if you need to Google that, because I'm not, weird decimals. There's no point. Anyway, so I'm going to convert the meters to feet and the minutes to seconds. So maybe I'll do part A, and then you can do part B on your own. How about that? Or you can check your work. As I said, meters to feet. So I'll do that first. So I'll put meters in the bottom, feet in the top. I know that 1 foot equals that many meters. You could have also used the other relationship. You know what I mean? Like, what is it? Like 3 some feet is equal to 1 meter. You could use that one too. It's the same thing. In any case, the meters cancel, and now I'm in feet per minute. But as I said, I want to be in feet per seconds because the question is asking me how many seconds it will take for the person to go 2,048 feet. So it makes the most sense just to put it in seconds, and then I'm good. So we'll do it right here. And it's not too bad, right? Put minutes in the top, seconds in the bottom. Now minutes cancel, and I'm now in feet per second. And then, of course, there are 60 seconds in 1 minute. And now everything should be good, because as I said, I have only feet per second, and I just need to multiply all this out. So this is equal to 1,000 80. That's the only number in the top besides ones. And then the bottom, I get 0.3048 times 60. And this is feet per second. All right, so let's see what that number is. We can just plug in our calculator. So 1080 divided by 0.3048 times 60. So what do I get? About 59, I'll say 59.1 feet per second. All right, but we're not done yet. So basically all we've done so far is convert the information that we were given to make it compatible with the question. So I converted the height of the tower into feet, and then I converted the speed of the elevator into feet per second. Again, because I knew the height in feet and I wanted my time in seconds. So we're just making things work together nicely. And now I can actually get my answer. So the time, so it's a little tiny here. So the time will be, so the way this will work is that you start with the distance you want to go. So 2,048 feet. And you can think of this as sort of a relationship between its feet per second, right? So every 1 second, you go up 59.1 feet. So it's a relationship between time and distance. So what it allows you to do is convert distance into time and vice versa. In this case, we want to go distance to time. So that's what I'll do. So multiply it times feet in the bottom, seconds in the top. As I said, 1 second is you go 59.1 feet. All right. And just like with all the other unit conversions, the feet cancel. And I'm left with seconds. So let's see what we get. We get this number, 2048 over 59.1. So, so 2048 divided by 59.1. So hopefully, if we did everything right, it should be about 34.65 seconds. All right. So again, and this is, I don't know if I feel like we did a problem like this when we were doing units. I can't remember. Usually I do one like with a baseball or something, or a bicycle, but it's no different than converting like feet to inches or anything like that. Basically, you have some relationship. Again, you're using feet per second. So this many feet equals this many seconds. In this case, 59.1 feet equals 1 second. And we're just converting distance to time. But you could have gone the other way. If you wanted to know how many feet he traveled, say in like 70 seconds, you would multiply the seconds times 59.1 over 1. So basically the reciprocal of this, and it would have given you a distance. So you can use this speed as just a relationship between time and distance. So you can always think of it in terms of unit analysis, which is kind of interesting, and you don't usually do it like that. But you can, which is fun. Right?
Oh, for the bottom question, part B, instead of doing meters and minutes, you could do miles per hour.
Yeah. So for part B, basically it's just asking you to convert the feet per second into miles per hour. Or if you want to do everything again, it wants you to convert the 1,080 meters per minute into miles per hour. Right? But you can save yourself some trouble, right? So up here, we already converted the meters per minute. We converted that into feet per second. And so you can use this 59.1 feet per second. So convert 59.1 feet per second to miles per hour. All right. And it's the same thing. So it kind of, if you use what you used for this first part, for the second part, it saves you some time. Otherwise, you have to redo this a little bit. But you can also just rewrite that. So you will have 1080 meters over 1 minute. Then you'll convert the meters to feet like we did. And then you put another little conversion factor in here where you convert the feet to miles. And then the only other difference would be you'd convert the minutes to hours instead of seconds. So this part B will be very similar to what we did up here. Yeah. Any other questions?
I had a question. Now this is all seriousness, because of my love for physics. Is this the same process that you would find if you wanted to figure out the factor if he was plunging from the 128th feet to the first floor,
That's
or
a,
in many cases to the basement.
that's a little more difficult. Like if you mean like if like an object in free fall,
Yeah,
so like suppose it was a guy falling off a roof, which is mildly morbid.
yeah, roof
But
or elevator. Yeah, same
yeah,
difference.
yeah, no, it's a little different. So, and the
Uh,
important difference is that the elevator is moving at a constant speed. Like it's at a constant speed of 1,080 meters per second, and that speed's not changing because it's just a motor pulling it.
right.
Or I don't know how elevators really work, but it's just a
Yeah.
motor running at a constant rate. Whereas a person falling, you have gravity accelerating them as they fall. So to
Yeah.
find out the time it takes for a person or an object in free fall is going to be a little more difficult, just because their speed is actually going to increase as they go. And if you want to get
Very
even
true.
more difficult, even if you want to make it
Yeah.
more complicated, you can consider things like suppose someone jumps off a really tall tower, right? Or make it less morbid and so you drop a ball off a really tall
Yeah.
tower. Um,
Yeah.
then,
Yeah.
then so the object will also have wind impacting it, and it also has something called terminal velocity. So gravity will pull it down and increase its velocity up to a certain point, and at that point, which is called terminal velocity, its velocity won't increase anymore. Um,
Yeah.
I don't
I see.
entirely understand it that well because
Yeah.
it's mainly physics, but yeah, I know at least that it's going to be a different situation. But it is a good question.
Yeah, I didn't take all that into consideration, but now that
Yeah.
you laid it out, I can see where all the other factors would come in.
Yeah, it's a little more difficult.
Yeah.
But yeah,
Especially
so
in a shaft though too, you've got a little bit of a cushion of air as it's rushing upwards.
that's a cool question too. I don't know how that would work. Like, suppose that the elevator, like someone cuts the elevator right at the top and
Yeah.
it free falls. So it's gonna accelerate because of gravity, but you also have that cushion of air at the bottom, and I don't know
Yeah.
how airtight the elevator, whatever they are, or canals
Yeah, I'm
are.
not really sure either.
So I don't know.
JCC,
Yeah.
at JCC on campus, I could actually put my hand next to the seams as it's going up.
Mhm.
The elevator was coming up, and I could actually feel the rush of the air coming out.
Yeah. That it probably would impact it. I don't know
Yeah.
how much it would impact it, but
Yeah.
that's a good question. That's kind of cool. Yeah, I don't know.
Yeah, like I said, it comes from my love of physics. I mean, I can't really comprehend it, but I know how big an atom is, compared to a planet. Things like I can visualize it, but the mathematics side of it is a little bit more problematic.
Yeah. Yeah, no worries.
I think Einstein actually envisioned it the same way, in a way, because he had a disability in mathematics.
Yeah, I don't know. I know he did a lot with math, but and physics, once you get too far out of like just simple mechanics, I have no idea.
Yeah. Yeah.
Anyway, so I also wanted to go over 8. Again, I'll sketch it. We'll do some of it. All right. So, and this one is just, it's another one where we're doing unit analysis, and it might not seem like unit analysis, but it is. So let's give it a go. Let me move this out of the way. I don't like, so when you using Zoom and the chat, you have the chat box up, it won't go away when you click on another. I don't understand why that is. Anyway,
Yeah, if you click on the arrow, you can click, it says close or pop out. You just have to click close and it goes away.
click on the arrow. Huh. Wait. Oh, I'll figure it out. I'll figure it out one day. I'll try that later. Anyway, so this one again, it's unit analysis. It just might not seem it. So the Earth is 4.5 billion years old. Yada yada yada. Suppose you represent the entire history of the planet by 12 hours on a clock. So the entire history of the planet. So basically, what I'm saying is that 4.5 billion years equals 12 hours on a clock. So it's just 12 hours. Right? That's like our conversion. That's like 12 feet equals, 12 inches equals 1 foot. And then I give you some more information here, like the birth of the Earth at the stroke of midnight. So like, again, imagine, it's probably easier with like a physical clock. Wait. So I have a bird clock. If you don't have a bird clock, I advise everyone buy a bird clock because this one doesn't have batteries in it. But when you get to an hour, it makes a bird noise, and you wouldn't expect it to be as pleasant as it is. Anyway, so 12 o'clock is the wild turkey on this clock. And so at 12 o'clock, wait, I can do this. At 12 o'clock, that's the birth of the earth. And then 12, as we go around, as we spin it around, I'm not going to spin it all the way, but it's trying to do bird noises. As we spin it, we'll eventually get back to 12, and that's the present day. All right. So that's the setup. Again, highly advise a bird clock. And so what we want to do is first question, how much time on the clock represents 500 million years? And we're just using this conversion factor. So I have 500 million years. All right, I'll start with that. I'm going to just convert it by doing 4.5 billion years. All right, and it's kind of like, it's like the bike path problem. So it's going to be a million years like in history, like historic years. And these billion years are like historic years. Like you're talking about the entire history of the planet in years. And so those years cancel. And then in the top, and this is 4.5, sorry, I missed the decimal. And in the top, we just have hours, 12 hours. All right, so you're just like scaling everything down, just like with the bike path, but instead of distances, we're doing it with time. And that gives you some answer, all right? And in hours. And then, so that will be the time on the clock that corresponds appropriately scaled to 500 million years or 500 million years. Now, for the other one, it's gonna be exactly the opposite. So how long before noon does human history begin? So up here, I say human history extends back about 10,000 years. So what you do is you take that 10,000 years and just convert it using the opposite. So I'll have 10,000 years. And again, this is like historical. And then I'll just do times. And again, 4.5 billion years. And again, these are like historical. Like, so they cancel. And then the top, I just have 12 hours again. All right. And you'll get something, like maybe I'll do this one and we'll see what you can do the other one, figure it out. Like I already laid it out, but let's see if I can get everything in here. Ooh, there we go. So I get 10,000 times 12. The only weird part might be the billion. No, because we need to divide this by 4.5 billion. And so a million is 10 to the 6, right? So a billion is 10 to the 9. So what I'll do is and if you didn't know that, you probably could have put it in Google and it would have given you how many decimals it is, but million, billion. So you go to a million, everyone knows what a million is, like into 6 zeros, right? And then you just do 3 more. So I have divided, so it kind of goes back to some scientific notation stuff. Divided by 10 to the 9. That's, and 4.5. So it's 4.5 times 10 to the 9. So that's 4.5 billion years, because again, 10 to the 9 is billion. And then we have 4.5 of them. So you don't need to do it like that, but it's a nice way. So you get that. So, so again, this is, if you're using this kind of calculator, even if you're using one of these calculators, I think it will also spit it out like that. It's scientific notation, right? And we've done this. So this is, you can write it as 2 point, I'll just round it as 67 times, so it's E. And we mentioned this before, but the E just tells you it's 10 to whatever comes after the E. So it's 2.67, again, I rounded, times 10 to the minus 5. All right. So it's tiny, but it's not too tiny. And this is in hours. So it's not super helpful. Like this is an answer. And I mean, you could have left it like this, but there's a better way, right? So this is a decent problem because it hits several of the things we did at the end, right? You could use scientific notation to answer it. You're using unit conversions. And lastly, you could, again, if you did it really well, you could kind of get into rewriting things in ways that make more sense and are more easily understandable. So like 2.67 times 10 to the minus 5 hours isn't too great, right? So what we can do is, again, I wouldn't expect you to necessarily do this, but you could convert it into minutes or even seconds. So to convert it into minutes, I just multiply it times 60, right? 60 minutes in an hour. So times 60. So you get 0.0016 minutes. So even that, I think even that is an improvement. But if you wanted to be even better, it's still, what is 0.0016 minute? I have no idea. But you could convert it into seconds. And so it's 0.096 seconds. All right. Which is better, right? So basically, this is, if you round it, it's about 1/10 of a second. Well, it's 9/10 of a second. But, or it's 9/100 of a second? I don't know. But if you round it, so it's about 0.1 seconds. There it is. That's about 1/10 of a second. That's what I was meant to say. So about 1/10 of a second. All right. So again, this problem, just like the bike path problem, is just trying to get you to better understand how to deal with numbers that are kind of odd. So especially this last part. For the first part, I don't think you really need to do much because 500 million years is decently large. But for here, since we're converting 10,000 years, it's a little more difficult because it's so tiny compared to 4.5 billion. But the point's the same. So you do the conversion, and again, this is sufficient answer, but a better answer is about 1/10 of a second. And again, keep in mind what that says. So it says, how long before noon does human history begin? And so if I have my bird clock, you would go back to noon. Sorry, let me just go back. All right. So it's at noon, give or take. And the human history, the entire thing is the history of the Earth, 4.5 billion years. But relative to the scale, human history steps back like 1/10 of a second. So you know, what do we have, hours, minutes, and this thing's your second. If it's not functioning, but it should tick along, right? And so 1/10 of one of those little ticks represents the entirety of human civilization, essentially. And that's the goal of this problem, is just to scale an unknown quantity and make it more understandable. All right. As I said, you can do just finish the computation, you should be fine. All right. Any other questions from the homework, or any ones or not the homework, the tasks that you had difficulty with? Again, I don't really mind going over some of these, especially these ones, because they're a little funky. All right, so let's get into the notes then. Here we are. There we go. So 4.2, 4.3 today. I don't think we'll finish. It's only 4:30, but we'll get a good start. We'll at least finish 5.2. All right. So, oh, I forgot to show you. I needed to end. Just a second. Where did we go? When we ended last time, we were talking about this, right? And I started computing some of them, and I told you I would just finish it on my own and show you on Tuesday. So here we are. And let's recall what we did, right? So we were talking about compound interest, and we did talk about this when we did exponentials, but in my notes, I only counted one example where we did this, so I wanted to kind of do it a little more. So here's a big, long example. And so what we did is we have month one. This is the money we started with, again, called the principal. And the interest rate here was, I think it was 5.2%. Yeah. So again, this is the last page of last week's notes. So we ended, and it was 5.2%, and that's the annual. So remember some of these definitions, right? APR, annual percentage rate, is the amount of interest that you get over the entire year. You don't get a dime more or a dime less. You get exactly the APR over the entire year. And so when we start doing these when we start computing interest on a monthly or a weekly or a daily basis, basically anytime more than once a year, we have to take the APR and break it into tinier pieces of interest, because we can't have more interest than the APR. So when we start doing, we're doing monthly in this example. So when we do monthly compounded interest, you take the APR and divide it by 12 because there's 12 months in a year and you're doing it 12 times. And when we did that, we got 0.43%. All right. So on my long example here, let me just make sure everything's good. All right. I keep getting these bad internet symbols. I don't know what that means. But so we took our principal and we computed 0.43%. So 4.43%. So as a decimal, you have to be very careful. A lot of people, when they see 0.343%, they might already think it's a decimal because there's a decimal sign there, but it's not. It's a fractional amount of a percentage point. So you still have to convert it to a decimal by doing 0.43 divided by 100. All right, so this is it as a decimal. So it's equal to 0.0043. So we're talking about a very small amount of interest. It's very tiny. But again, it's computed every month. So that's why it's so small. Over the entire year, you'll still get 5.2%. And as we'll see, actually more than that. Anyway, so principal, I computed 0.43%. So I multiplied 2,200 by 0.0043. You get that number, right? I took it, added it to 2,200 to get this number. And then I repeated, all right? It's like rinse and repeat. So I took this number, took 0.43%. That's this. I added it back to the principal to get the next month's principal. And then you just keep repeating, as I said. And as you'll know, and we kind of grow by about 4 cents every month. Like, I forget who it was, noted that on Thursday, that it seemed to be growing at 4 cents every month. It's not quite at 4% though. Like here we grow by 5, here we go by 5, and we kind of go down. Some of these might be rounding related, because when I was computing these, I did round. So some of these could be related to rounding. In general, it should go up. At the end, you notice we're going up by 5. I don't quite, I think it's kind of rounding. It will get bigger as you go. The problem here is that we're dealing with such a small amount of interest and a small principal. So it's going to grow really, really slow. Anyway, what I did once I computed all of these, doing that iterative process I just mentioned, is I totaled up how much interest I had. And well, I guess I did it throughout. Sorry. Well, I didn't actually do anything. I just kept adding it. Sorry. So now the last interest, added it back to the principal to get this amount. If you wanted the total interest, you could do that too, but I don't think I did. Anyway, so that's what I get in the end when I do these 12 compoundings, again, once a month, and I add it back in, do the next month, add it back in, do the next month, so on and so forth. Now, so this is with compound interest. So now let's compare it with the simple interest. So if you remember, simple interest is when you have a principal and you just multiply it once by the APR. So in this case, I have 2,200 and I'm taking 5.2%. All right, so I multiplied 2,200 by 1.052. The 5.2 corresponds to 5.2%. And then the 1 just corresponds to the fact that I'm adding on the interest all in one go. We did this a little bit when we were talking about percentages more. But in the end, I get 2,314.40 cents. And so you'll see that doing simple interest, you don't gain as much interest. So in this case, I only lost $2 because with the compounding interest once a month, I got $2,316.29. So it's like a little over, it's like $2, a little less than $2 maybe. No, maybe, I don't know. It's like $2. And so it doesn't really matter much here. Now, if we had a huge principal, if we had like $3 million in here gaining 5.2% interest, we would obviously want more compoundings than one. You'd have much more money if you had a bigger principal. Since we only had 2,200, it's not as much, all right? Anyway, that's what we ended with last week. And it's good we kind of reviewed some of our terms. So what I want to do now is we want to describe a formula for that process, right? So we already did this really when we did exponentials, but just to jog our memories, remember what we're doing, right? I'm adding 0.43% interest every month. So really you can take this number, right? Multiply it by 1.0043 and you'll get this one. You can take this number, multiply it by 1.0043 and you'll get this one, and so on and so forth. So a really quick way to do all this is to just keep multiplying by that 1 point, whatever your interest rate is, for as many times as you need. And we can express that all really concisely. So here's what we have. The setup here is P naught's our principal. We're generating compound interest at a rate R, and then we're compounding it n times a year for t years. All right, so principal, P naught, and just like I was telling you on that sheet, we're just gonna kind of repeatedly multiply it by our percentage as a decimal with the 1. So I'm gonna do it 1 plus, all right? And again, remember how we did the APR. We took the APR, divided it by the number of compounds per year. And then the number of compoundings per year is n for t years. So the total compounding is n times t. All right, and these are multiplied. So that will describe the compound interest. Right. That makes sense? All right. So let's try some examples with it. Again, it looks funny, but hopefully we understand where all these come from. Again, the rate is divided by n because it's the rate, R is your APR, it's your annual percentage rate. So we have to divide it to get the actual growth per whatever. All right, so I got a few examples here. Let's try this first one. You invest $12.50 in an account compounded, and you just want to pick out the information that's important. Compounded monthly with an APR of 3.4%. How much will you have in 2 years? There. And so let me rewrite what our formula is. A equals P naught, 1 plus R over N to the NT, right? So if we're doing things monthly, then we have 12 compoundings per year. So N is 12. Our interest rate is 3.4. So again, be careful when you convert things to decimals. Oops. So it's 3.4 divided by 100. It's 0.043. So R is 0.034. I think I said 43. 0.034, sorry. And then we can just plug everything in, right? Oh, and our P naught is the 1250. So we've associated all of our variables to what they belong to. Oh, and we want it in 2 years. So that's our T. So, pick out and kind of organize the information as it's given and then try to, answer the question. So, and A is the amount in the account. So that's what I want to solve for. So A equals P naught, which is 1250. 1 plus R is 0.043 or 0.034. I keep saying 43. 0.034 all over N, again monthly, so 12. All to the N, again 12, times T, 2. Right? So now you just compute it. It could be more complicated depending on your calculator. Some calculators, it's easier to do some of these things than others, but it's all possible. So I don't know. Sometimes I don't like doing all this in one step. So especially if you have a scientific calculator or I don't know, even more or less fancy calculator, I do it in different steps. So like for instance, what I can do is I can compute the things between the parentheses first. So 1 plus, well, here's what I can do. I can even do it simpler. I can start with the division. So 0.034 divided by 12 is whatever that is. Now I'll add 1. All right, so that's what's in my parentheses. Now 12 times 2 is 24. So I'll raise it to 24 power. So it's that. And then times it by the principal, 1250 times 1250. So that's what I get, about 1,337. And we're dollars right now. All this will be money related. So when you're rounding, generally we round to the nearest cent. So it's 1,337 and 83 cents. Sorry. Any questions? Cool. All right. So again, we're just going to play around with the equation a little, do some different examples that kind of do different things, just to make sure we're all familiar with how it works. So this one is similar. You invest 2,400 in an account, compound it, but now we're weekly. So think of how many times a year that's going to happen. How many weeks in a year?
52.
Yeah, right. So that's just going to be our N. Our N is just 52. The APR is 7.9, so our little r will be, again, you always want our r as a decimal, so 7.9 divided by 100, 0.079. Oops, sorry about that. There we go. 0.079. And then, is that it? Oh, and then principal's P naught is here, is 2400. And then we just don't know what T is, right? And so I give you 18 months. And so you might be tempted to put, oh, T is 18 months, but T is in years. T is in years. So how do I convert months to years?
18 divided by 12.
Yeah, you just divide by 12, right? And if you want if you want it to be really fancy, you could do it in like unit conversion terms, so 18 divided by 12, like, so that would just look like this: 18 months times months in the bottom, years in the top, right? 12 months in 1 year. And so the months cancel, right? So you could do it really like explicitly with unit conversion, but you don't have to. Hopefully, I mean, imagine it's obvious to most people that use 5 by 12. But you can also do it as a decimal, so you 1.5. And that's our T. All right. So the couple things I wanted you to note with this problem is that T can be a decimal and it can be fractional. So you don't have to have a whole year. T can be months, some number of months. It can be, I could give you compounded for 37 weeks and you'd want to convert that to years just by dividing by 52. So, whatever time amount frame you're given, just convert it to years using potential unit analysis, and then you can plug it into the formula, but you'll be good to go. So now your A, again, P naught 1 plus R over N to the N T. Then you just plop it all in. So 2400, 1 plus 0.079 over 52. So you're getting a very tiny amount of interest every week because you're 7.9% divided by 52. But you're doing it 52 times 1.5 times in total. So that's kind of the payoff. The more compoundings you do, the better you'll be off, essentially, up to a certain point, really. So I'll do it the same way. So 0.079 divided by 12 is some number. Oh, sorry, by 52. 0.079 divided by 52, not 12. So it's even a smaller number. Plus 1, and then to the power. And so here, I don't know what 52 times 1.5 is. So I'll put parenthesis 52 times 1.5. So I get that. Again, it doesn't look big, but you can kind of see what this is, right? So it's 1.1257 whatever. And so in terms of percents, what that means is that your principal is going to grow by about 13%, right? So times 2,400. So about 2,700. Again, round to the nearest cent because we're dollars. 0.69. Okay. It's kind of cool. Okay. Any issues with that one? Again, we're just trying to learn some of the details of how to use this. I might skip some of these, but let's see what we got. $4 in a compound. Nah, well, this one's too similar. This one, just note when you're doing something quarterly and it's 4, but you probably would know that. Let's do this one. This one's more interesting. The second one down here. This is page 3. So bank account has a 10% APR compounded semi-annually. So that means twice a year. After investing in initial principal, the amount of money after 7 years was $2,500. What was the principal? So this one is kind of different, right? We want to know the principal, P naught, knowing A, the time T, and the APR is 10. So my rate here, I'll put it over here. So if you need to calculate, you can just do it, of course. So 10 divided by 100. Ooh, you can't see that, 0.1. All right. So we're solving for P naught. Solving for P naught. So kind of be careful. Make sure you read it carefully. But you can set it up the same way, right? So I have A equals P naught. 1 plus R is 0.1. n is 2 to the 2 times 7. And then this a is 2,500. And so, hopefully it doesn't look too bad, right? I mean, this is kind of ugly, but we can simplify that, right? What I can do is I can compute this stuff. So let me do it over there. There we go. So I'll do 0.1 divided by 2 is 0.05, and then plus 1, 1.05, and then 2 times 7 is 14, so to the 14 power, so whatever that is. And so it's quite a bit, actually. But so I can write that in. So this is like P naught times 1.979931599. You can round it to whatever you like. The more you round, just whenever you round, you should realize that you're going to get errors in your exact, like it won't be, it's an estimate when you start rounding. So the more you keep, the better. But and now, so 2,500 equals that stuff. So what I can do is I can just divide both sides by that 1.9 stuff. So I get, let me just put there. So I do 2,500 divided, 2,500 divided, and there's a trick on these TI-85 calculators. So if you do second, what is it? Enter? No, where did it go? It's been a while since I did it. You can do second something, and it'll put the answer in for you. Oh, second this time. So you'll do 2,500 divided by, and then down here it says answer above in the blue, so you do second answer. And it will use whatever you got previously for answer. And so it's about 1,262, right? Again, you could have retyped it, but if you have one of these calculators, it does do some things for you. Right, so again, that was second and then like negative sign. Just look for A and S in blue. But, so that's it. So a P naught equals 2,500 over whatever that is, 1.9799, yeah. And so I got about, again, dollars, so round appropriately, 1,262 and 67 cents. There you go. Cool. So a little different. Any issues with that one? You're just plugging things in and solving for the unknown. Now, there are some situations, like if you're playing around with these and you try solving for like t, you might run into a pickle because we haven't done logs and we don't really do logs. Do we do logs? We don't do logs. I wish we did logs, but yeah. So if you're trying to solve for time, like, a question like you have $2,600 in an account with some APR, compounded by monthly. If you wanted to ask yourself how many years it will take to get like $6,000, you need logs really to solve for that. So we can't do that kind of question, but the other ones we can solve for by and large. Like this one here we'll solve for the APR. So let's try it. A bank account has principal is 6,500 compounded quarterly. So N is 4. This is my principal. After 10 years, the amount in the account was 15,000. So T is 10. What is the APR? Right. So as I said, we can't solve for the time T in the equation because we don't have logs, but we can solve for just about everything else. So here, I'll just plug everything in. So again, I'll rewrite the formula, P1 plus R over N to the NT. I plug in everything I know, right? That's just a generally good strategy. If you're given a bunch of variables and it asks you to find another variable, plug in what you know and see if you can solve for what you can't. So A is the amount in the account at the end, so 15,000. P naught we're given is 6,500. 1 plus R, I don't know what R is. That's my APR. But N is 4. And then N is 4, oops. And T is 10. There we go. So let's see what happens. So I'll rewrite it. Well, maybe I won't. I can divide by 6,500 both sides, right? So I get 15,000. Again, we're just trying to solve for R now. 15,000 divided by 6,500 equals, and what do I get here? I get 1 plus R over 4 to the 40th power. All right. And I don't know how familiar we are with like roots but we're gonna learn. So what I can do now is, like, let me move this for a second. So like, suppose I had this, right? Right. Suppose I had this equation, and I wanted to solve for x, right? I would take a square root of both sides. I would take a square root. I would take a square root, and I would get what x equals like 2 generally. X minus plus or minus 2, but we'll just say 2 for now. That's what you do. And this isn't any different. The only difference between this and this is that instead of 2 and taking a squared root, I'm 40, so I'm taking a 40th root, but the operations are identical. So the other way you can write this, by the way, is you have x squared equals 4, right? What I can do is, instead of writing it as a square root with the square root symbol, you can write it as a 1/2. So what I could do is I'll just take half power both sides of this equation. So I'll do like x squared to the 1/2 equals 4 to the 1/2. And what you're doing really when you do this is just like when we talked about with exponents. When you have an exponent to an exponent, you multiply the exponents. So the reason the half exponential power is the opposite of a squared power or 2 power is because when you raise the one to the other, they multiply and you get 1, so they cancel each other. So you can think of them as inverse operations. The one is undoing the other. So I have x equals just the square root of 2, which is plus or minus 2, depending. We'll just say 2 again. So that's the idea. So here, again, this one's a little tricky. Here, what I'm going to do is I'm going to take a 40th root. So it'll be 15,000 divided by 6,500, all to the 1 over 40. And that's equal to 1 plus r over n. Oh, 4. And this, it looks really bad, but just plug it in your calculator. Right? Never be afraid to just plug things in your calculator kind of blindly. So, so I have 15,000. Oops, yeah, that's good. Divided by 6,500, right? And that's something. And now I do caret, which is to the power of, and then I want it 1 over 40. So 1 divided by 40. And enter. It's like 1.0211. So this is 1.0211. I don't know. I'll leave it at that. And then this is equal to 1 plus r over 4. And now now this is much nicer, right? We've just kind of reduced all our anxieties. And now we can just solve this simple equation here. So I'll subtract 1 from both sides. So I get 0.0211 equals r over 4. And I just multiply both sides by 4. So minus 1 times 4. So r equals this number, just about. So 0.0845. All right. And it might look weird, right? But it's a decimal, convert to a percent. So multiply times 100. So your rate, your APR is 8.45%. So it's kind of neat, actually, because what it allows you to do, again, it's a little complicated. It's a little more complicated than the algebra we have been doing, but it's not too far outside of our comfort zone. Anyway, what it allows you to do is, if you want to generate a certain amount of money, like in some bank account or something, and you're like, how much interest would I need to do that? It allows you to do that in a certain time frame. So it could be something that comes in handy. I mean, I guess you can't really control the interest rates too much, so it's not something you have power over entirely, but it is, it's something that could happen. Anyway, so that's all the compounding interest. That's 4.2. But this is kind of 5.3 is called the annual percent yield, and it's the same thing. It's directly related to compound interest. So let's start talking about that. So the annual percent by which an account increases is called the annual percent yield. Annual percent yield, also known as the APY, for obvious reasons, right? APY. Where's my example? We're gonna use that example I had earlier, just in a second. If an account is compounded more than once a year, the APY will be more than the APR. If an account is compounded once a year, the APR will equal the APY. So basically what's happening here is that when we do compound interest more than once a year, you're going to gain slightly more money than if you had just done the simple interest or did the interest once a year. And that slight more money gives you a slight increase in the APR, essentially. Like you're getting more percent yield, more percent interest than you would just from the straight APR. So let's go back to this example here. Let me get a nice fresh sheet of paper. So in this example here that we did last week, and I talked about at the beginning of class, the compound interest once a month at 0.0043 or 0.43% gave us this much money, right? Now finding 5.2% gave us this much money. So let's see what happened here. So 5.2%, so 5.2% of my principal is 2,200 so let's just look at that. So 5.2% of that. So 2,200 times, and so 5.2 divided by 100. So it's $114.40. $114.40. All right. So that's just 5.2% flat. Now, if we compounded it monthly, what do we get? So we get this much money, and let's see what the interest is, right? I said it was about $2 more. So 2316.29 divided by 2,200, and then minus the tax from the simple one. Well, I guess we'll leave that. There you go. All right, so it's 116. So 5.2% compounded monthly is so 116.29. Sorry about that. All right, so if we compound it monthly, we get this much money. If we compound it just once by taking 5.2%, we get $114. So there's different, right? And so this is exactly 5.2%. And so what you can do is you can say, well, what is $116 as a percent of my initial principal, right? So all you would do is you do, did we talk about this? We must have. As percents, right? It's like part over the whole. So 116 divided by the whole. Oh, it would be relative change. You do the relative change, right? So it'd be, let me do that again. So it'd be the new amount over the old amount. That gives me the interest. And then you divide it by the old amount or the initial amount. So divided by 2,200. And then you multiply by 100 to get it as a percent. So this number here is actually 5.28, I don't know, 59 maybe percent. So that's the difference here. So the 5.2 gives you that much, but if you compound it monthly, you're getting a little more. And as a percent of the initial principal, it's a little more. It's a fractional amount, but it is slightly more, right? 5.2 versus 5.28959. It's just a little more. Right? That's what APY is. All right. So back to my notes. So I already told you how to, I just computed the APY. So it's going to be basically the not the relevant, what did I just say it was? Relevant? Relative, that's the word. Relative change in account. Right, so it's going to be the, I don't want to say, so it's going to be the new amount. So it's going to be P naught 1 plus R over N to the NT, right? So that's the new amount in the account. That's the balance of the account after T years, minus the initial P naught all over the initial P naught. So this is the APY. And it looks really bad, right? But it can be simplified. Just you can cancel all the P naughts everywhere. So that cancels, that cancels, that cancels. And so I just get 1 plus R over N to the NT minus 1. All right. And so that's a formula you can use to compute the APY. Right. So I have a sheet here somewhere. Okay, okay.
Where do you get the -1?
Oh, from here. So I should factor it. So when you factor out from the numerator, you get P naught. Because when you this is really bad notation, but sometimes people like to do it. Uh, so when you cancel things like this, you're actually factoring out a P naught from everything in the numerator, and then everything in the denominator. So for instance, I'll factor from the numerator, and I get 1 plus r over n to the nt, and then -1. And then the bottom, I just get P naught, I don't know, times 1. And then I cancel those. And so in the bottom, I get 1, which you can ignore. But in the top, I still have that -1. And that's where it comes from. It comes from that P naught there.
That makes sense.
Cool. Yeah. Yeah. So usually, I don't encourage you to do this kind of thing where you cancel just haphazardly. I would always advise you to factor out anything you're canceling, because like you did, a lot of people will cancel something and think it kind of disappears, but it doesn't. You're replacing it with a 1. And so it's still there, but sort of not. All right. It's a good question though. All right. So that's a good formula. And so we can use this formula up above in this example I had. So let me just rewrite it. So the APY equals 1 plus r over n to the nt minus 1. Okay. And like here, you'll note, I don't give you the principal at all. I don't give you the time either. I need to give you the time. What's the APY for an account compounded monthly? I don't know, for a year. Right. So let's see. So because you'll note the t is still in here, but no P naught. So you don't need the initial principal to compute the APY, but you do need everything else. So it's 1 plus R, which is 9, so it's 0.09, and then N is monthly, so it's 12. All to the 12, and then for a year, so it's T is 1. Times 1 minus 1. Let's see. Again, there's not much you can do here as far as like hand computations. So 0.09 over 12 plus 1, all to the 12. Oh, I'm sorry, I divided by 12. That didn't look right. Let's try that again. 0.09 divided by 12 plus 1 to the 12 exponential. Be careful using the right operation. There you go. And then minus 1. So it's that 0.093. I don't know. I'll say 0.094. And it's APY, it's a percent yield. So usually you consider it as a decimal, kind of like APR. It makes more sense as a decimal. So times 100. So it's about 9.4%. As I said, the APY will only be slightly more than the APR, because the amount that you get from compounding interest isn't really that much unless you have a lot of principal over a long time. All right. Let's just do one more and then we'll end because it's already 5 o'clock. All right. So what's the APY of an account compounded daily? We haven't done any daily yet. At that percent. I forgot the word at. So just remember, APY equals 1 plus r over n to the nt minus 1. And I didn't give you the time here either. So I needed, I don't know, maybe for 3 years. See, I wrote these Monday, and sometimes when I write them early, I don't think. So let's see. So 1 plus, my rate is 6.5%. So it's 0.065 daily. So 365. All to the 365 times 3 years minus 1. All right, so it's kind of one of those situations again where like your AP, your rate, your little r is going to be super tiny because you're dividing it by 365, but you're then multiplying it, you're taking it itself 365 times. So yeah, it can work out. Let's see though, let's see what happens. So 0.065 divided by 365, that's a lot of numbers. So it's very tiny. It's e to the minus 4 plus 1. And then it's all to the power of 365 times 3. Again, make sure you put it using the caret or whatever your exponentiation is on your calculator. And it's decently large, right? Like, look at that, 20, 21, I was pointing with my finger, 21, 20, 22%. and then -1. There you go. So it works out to be about 0.2, I don't know, 215 maybe, which is, as I said, 21.5%. It's decent, right? Oh yeah, and you bumped by 100. Like that's a lot. I mean, your rate was 6.5%, but that's quite big. I'm surprised it's so big. It's probably because you're doing it daily, so you're compounding a lot. As I said, the more you compound, the better you are, because that interest is being added back in as you kind of go. Today, Tuesday. So Thursday, what we'll do is we'll talk about something called continuously compounding interest, which is really interesting. And if you ever take calculus at some point in your life, you'll be able to understand it a little more, just because we need something called limits to kind of really get it. But basically, continuous compounding interest, what that does is, here we're doing it daily or weekly or monthly or whatever, but continuously compounding interest allows you to instantaneously take your interest and inject it back in the principal. And it's not doing it daily or yearly or anything. It's doing it like instantly every second of every day. And it's not even every second, it's like every millisecond. It's like always compounding, which is kind of a weird concept. And as it turns out, so basically the idea what we're going to talk about on Thursday is that this process of like doing things daily or, you know, every second even, will eventually like peak. Like it will only generate so much interest. So you might say, oh, if I compound more and more, I'll get more and more money. But unfortunately what happens is that you hit like a roof, like a ceiling, and after that, nothing happens. Well, not like nothing happens, but you won't gain more money through the interest. It's really, really interesting. So we'll do that Thursday. But any questions about this stuff for now? APR, APY, compound interest. We good? All right. So let me know if you have any questions on the test besides the one I did. But if not, I think we'll talk on Thursday. All right. Have a nice night, everyone.
Hey, Matt,
Yes.
I have a question about the test.
Oh,
The two questions that we went over, 2 and 8, I got the right answer.
Uh-huh.
I just did it a different way. Will I still get credit for that?
Yeah, it's
have
okay.
you looked at it?
No, it's
Okay.
it's fine as long as you get the right answer. I mean, as long as you're doing it in a way that's not like really weird, like as long as it's clear that you're not like just copying answers, then it's fine. Yeah, I don't
Okay.
really care how you do it. Yeah.
Okay.
Yeah, no worries.
All right. Thank you.
No problem. All right.
Bye.
Ciao.